Okay, section 5.3, so we're done with systems of equations. We're going on to something different here. It is called partial fraction decomposition. And there are 4 cases that we want to cover here. As you can see, distinct linear factors, repeated linear factors, non-repeating quadratics, and repeating quadratics. So all 4 of those cases we want to cover here in section 5.3. So this section is going to test your knowledge of rational equations. We're going to use what we learned in chapter 1 to solve these partial fraction problems. All right, so the 4 cases we just talked about, let's talk about the case 1, which is non-repeating linear factors. So you can see this description on page 541 for the setup. So what we're doing here, let's look at an example. Our task here is to change this given fraction, and notice in the denominator we have a linear factor of x minus 3 and another linear factor of x plus 4. This is what we mean by non-repeating linear factors. This x minus 3 factor, it only appears once. Okay, if it was squared, that would be a repeating linear factor, but it's not. It only appears once. X minus 3, we have another linear factor. It appears once. This is non-repeating linear factors. Our goal is to split this up into what we call partial fractions, right? We're taking one fraction and we're splitting it up into 2 or more fractions. In this case, for non-repeating linear factors, you can see again, the setup is on page 541. We're going to have one fraction for each of those non-repeating linear factors. So our task is to come up with the values in the numerators, right? So you'll be given this, and you'll be asked to decompose this using partial fraction decomposition. The answer, this is the question, this is the answer. Okay, we got to come up with that A and B to finish it. But that's, sometimes people say, what is being asked here? This, you're given this, you're asked to come up with this. And so we got to come up with that A and B. So what we do is use techniques from chapter 1. Remember what we did whenever we had a linear equation, we came up with the least common denominator, and we multiplied both sides of the equation by that least common denominator. Well, the least common denominator for these problems is always going to be the original denominator over here. Always. Okay, so least common denominator here is always going to be the original denominator. You don't want to multiply it out, leave it in factored form. So that's our least common denominator. So we're going to multiply both sides of the equation just like we did in chapter 1. I'm going to put it over 1 just to make everything a fraction. And then I'm going to multiply this side also by that. Okay, so I'm multiplying this side, and I'm multiplying this side. Right? Now this side, the denominator cancels with the numerator here. The x minus 3 over x minus 3 is just 1. X plus 4 over x plus 4 is just 1. So always you're just going to be left on the left-hand side with that original numerator. So let's come over here and you multiply that out and get 5x minus 1 on the left-hand side. On the right-hand side, you're multiplying this fraction times this fraction, and then you're adding to that this fraction times this fraction, distributed properly, right? So you multiply this fraction by this one, the x minus 3's cancel out, you're still left with the unknown a and this factor of x plus 4. So we get a times x plus 4. And similarly, this fraction times this fraction, the x plus 4's cancel out, we're left with the b and the x minus 3. Okay, now we want to distribute the A and distribute the B. So nothing happens on the left-hand side. Over here we're going to get AX plus 4A and BX minus 3B, once we distribute the A and distribute the B. At this point, we want to gather similar terms on the right-hand side. So remember, similar term has the same variable raised to the same exponent. So this and this are similar terms, the AX and the BX. There's no X in these. Remember, A and B are the numbers we're trying to come up with. So this is a constant term. This is a constant term. We want to put those together. So here we got nothing changed on the left-hand side. We're going to put the X terms together. And we're going to put the constant terms together. Now we're going to factor out the X here. There's nothing to factor over here. So 5x minus 1, we take an X out, we get A plus B. Right? AX plus BX. And over here we still, nothing to change here. All right, so again, what did? We took the original function, or the original fraction, split it up according to the formula for non-repeating linear factors. This side of the equation is going to change depending on what we have here in the denominator. In this case, they're non-repeating linear factors, so this is the 7. You can see that on page 541. So we multiplied both sides by the least common denominator to get rid of that denominator. We distributed, we gathered similar terms, and we end up with this. Now this is going to lead us to a system of two equations with two unknowns. Right? For this equation to be true, okay, to be true, the number in front of x on the right-hand side of the equation has to be the same as the number in front of x on the left-hand side. Right? So 5x, this has to be the same. A plus b has to equal 5. And the constant term has to be the same as this constant term. So 4a minus 3b must equal -1. So now we've created a system of two equations with two unknowns, and we know how to solve that, and that's all we're doing. So now we solve this system. Of two equations with two unknowns. And we know how to do that. This one, again, you can use either method. Let's go with substitution. We'll call this equation 1. We'll call this equation 2. So I'm going to solve equation 1 for either of the variables. Let's say A. So that's going to be 5 minus B. And then I'm going to plug this in to equation 2 for A. And I'm going to get 4 times A minus 3 times B equals -1. I'm going to solve that equation. 20 minus 4B minus 3B. So I get -7B is -21, and B equals 3. And if B equals 3, A equals 2. So your answer is this part here, plugging in the correct A and B. And once again, you'll be given this, you'll be asked to decompose it using partial fraction decomposition. You go through this, and your answer is the A value we said was 2, and the B value was 3. Good times. Now, if your values come out to be negative, like say if this was a -3, I generally just leave the plus sign and put the negative up here. If you put a negative and a +3, I mean, that would work too, but I usually just leave the plus and put the negative in the numerator if it happens to be negative. All right, so that's the first case, non-repeating linear factor. So the only thing that's going to change in the coming 3 sections is what kind of factors we have in the original fraction. Again, this was non-repeating linear factors. And depending on what type of factors these are, the form of these numerators are going to change a little bit. All right, so the next case is repeating linear factors. And that one is explained nicely on page 544. So second case, repeating linear factors. And again, that is nicely explained. Repeating linear, page 544. Okay, so let's look at an example of that. Here, this is checkpoint 2 on page 545. We have an example of this. You are given this fraction and asked to do the same thing we did last time, except as you can see on page 544, we get a fraction for each of the linear factors, and if they're raised to a power other than 1, like this x minus 1 to the first gets its own fraction on the right-hand side, and x minus 1 squared gets a fraction also. So you can see the difference between case 2 and case 1, how to set it up. Okay. So here we're going to have one fraction for the first. Think about this, you can think about this as x plus 0. Just because it's sitting alone, it's still a linear factor. It doesn't have a number associated with it, but you can think about it as a 0, right? X plus 0. That gets a fraction, and that only appears once, so that just gets 1. The x minus 1 appears twice, so it gets a fraction for x plus 1 to the first, and a second one for x plus 1 squared.
X minus 1?
X minus 1, thank you. Okay, so the x minus 1 appears twice, so it gets one fraction for the x minus 1 to the first power, and another fraction for x minus 1 to the second. If it was to the third, it would have another one for the third. And now everything, it's exactly the same process, except it's going to be a little bit more because we got 3 fractions instead of 2. So again, we're looking for A, now we're looking for 3 numbers. So we're going to get 3 equations and 3 unknowns. Okay, but it's exactly the same process as what we just did, just a little bit more algebra involved, and it's a 3 equation system instead of 2. So least common denominator here, again, it's always going to be the original denominator. We multiply both sides by that least common denominator. Left-hand side, always the denominator is going to cancel with the numerator, and we're just going to be left with the original numerator. Left-hand side, right-hand side, this fraction times this fraction, the x cancels with the x, we're still left with the a and the x minus 1 squared. A and x minus 1 squared. Second fraction in our set of 3 here, this fraction times this one, we get a b, we get the x, and we get one factor of x minus 1. Right? One of the x minus 1s cancels, but we're still left with 1, x minus 1. And then here, we're left with the c times x because the x minus 1 squared cancels out. Again, this is exactly the same as what we did in the previous example, it's just a little bit more involved. So let's expand this, distribute over here, and gather similar terms just like we did in the previous example. So now we get a, can avoid the most common mistake in algebra and multiply this out carefully. Make sure you don't forget that middle term of negative 2x for x minus 1 squared. Right? This is x minus 1 squared. Here we're going to get b x squared minus b and plus cx. And then we'll distribute the a over here, and then we'll gather similar terms. The 2ax plus a bx squared minus b plus cx. All right, so now we will gather the similar terms on the right-hand side. So the x squared term, we have an a plus b on the x squared. So let's just kind of skipping a step here and factoring out the x squared immediately from the ax squared plus bx squared. Becomes ax squared plus bx squared. The x terms, we get negative 2a plus c. Right? Those are the only terms with an x to the first. X to the first. So we say negative 2a plus c. So again, I'm going to put everything as plus, and then in parentheses deal with the negatives. So I get negative 2a plus c on the x term. And the constant terms, all I have are a minus b. So again, plus a minus b. Okay, so these are the terms with x squared, the a and the b. The x term, negative 2a plus c, and the constant terms a minus b. And now again, we're back to where we were. We're going to set up now a system of 3 equations. Now there's no x squared term over here, so think about it as 0x squared. Right? So we can come up with the solutions here. So the a plus b has to equal 0. Right? The number in front of x squared on the right-hand side has to be the same as the number in front of x squared on the left-hand side. So a plus b must equal 0. That's our first equation. Negative 2a plus c has to equal 1. Negative 2a plus c must equal negative 1. That's our second equation. And a minus b must equal 2. That's our third equation. Okay, so just like the first example, first we go through the decomposition, breaking it up into the appropriate number of factors, multiplying both sides by the least common denominator, which is always the original denominator, getting rid of the fractions, gathering similar terms, and setting up our system of, in this case, 3 equations and 3 unknowns. Now, generally on these, even though it's 3 equations and 3 unknowns, it's going to be a little easier to solve than what we looked at in 5.2. Like this one, we've already got nicely set up a system of 2 equations and 2 unknowns without doing any work at all, right? So we can just choose 1 and 3 and eliminate the b's. You go through any method you want at this point for 3. Actually, we only talked about one method, right? Elimination method. So that's our only choice. But sometimes, you know, we don't have 3 unknowns in this equation. We only have 2. We only have 2. We only have 2. That makes things easier. Sometimes people will look at this and say, well, wait a minute, there's not a c here, there's not a b here. That makes it easier. That doesn't make it harder. That makes it easier. So realize that. So here, if you look at 1 and 3, again, we can easily eliminate the b's and solve for a. So choosing equation 1 and 3, eliminating b. We get a plus b equals 0 and a minus b equals 2. We add those together and immediately we get one of the 3 unknowns. A is 1. Now once we know what a is, pretty easy to find b using either this or this. We'll come up here, put into equation 1 and get 1 plus b equals 0, which now gives us our b value. And once we know a and b, we don't even need both to find c, all we need is a. So we'll plug a into 2 and get negative 2 times 1, clear here, negative 2 times 1 plus c equals negative 1, so c is going to be negative 1 plus 2, or 1. So a is 1, b is negative 1, and c was 1. So again, this is the given fraction. You're asked to come up with this as your answer. This is the answer to this question. All right, so it looks like a lot of work, but just do one thing at a time, right? Multiply both sides by the denominator over here to get rid of the fractions. Gather similar terms. Set up your system of equations. Solve that system of equations. Finish by plugging those values into the right-hand side of the partial fraction decomposition. All right, so that is case 2, repeating linear factors. Third case, we start looking at quadratics. Again, the process is the same for all of these. The only thing that changes is the form of the right-hand side of the equation. So third case, we're looking at non-repeating quadratics. And this setup is on page 545. So again, this is what changes is the form. The idea really doesn't change much. So let's look at checkpoint 3 on page, actually, let's look at here we go. Non-repeating quadratics. Let's look at number 22. All right, so number 22 on page 550. We have a non-repeating quadratic example. So we have x over x plus, actually this is repeating linear, sorry, that's no good. That doesn't work. Where are we? It's a repeating quadratic. That's a linear and a quadratic. Let's see, got to be a good example in here somewhere. Okay, let's look at this one. So this is a combination of, sometimes you get a combination of the different cases. Let's look at this one so you can see exactly what's going on there. So here we have this quadratic expression in the numerator. We have a linear factor of x minus 2, and we have a quadratic factor of x squared plus 2x plus 4. All right, so this is going to be a combination of the first case and the third case. Notice we have one linear factor and we have one quadratic factor. Neither one is repeating. Each one is raised to the first power. So what happens here is we're going to get one fraction for that linear factor, and then we're going to get another fraction for the quadratic factor. Now notice when we have a linear factor in the denominator, we have a constant term in the numerator, right? 1 degree less. Think about it like that. This is degree 1 polynomial, 1 degree less. What we did in the first two cases, we had constant values in the numerator. Now we have a degree 2 factor in the denominator, so what goes in the numerator here is a linear factor. Think of the most common linear equation, mx plus b, right, is slope-intercept form. That's what we're going to put in the numerator of a quadratic factor, is a linear factor with a constant on the x and a constant for the constant. So linear factors get a constant in the numerator. Quadratics, which are degree 2, get a degree 1 expression in their numerators. And again, you don't need to memorize these things. This is explained on page 545, this setup. Sometimes I'll even give you this and just ask you to solve for A, B, and C. But you should know how to set it up yourself. And now again, exactly the same method as what we used earlier. We're going to multiply both sides by the least common denominator, set up our system of equations, and solve exactly the same way, just being careful, paying attention to detail, doing one thing at a time. Let me do it that shot. All right, so our least common denominator here, again, is just this. Multiply the left-hand side by that, multiply the right-hand side by that. All right, so now it's really just practicing your algebra, practicing, making sure you know how to multiply correctly, factor, everything nicely. So this factor cancels with these factors, left-hand side, we're just left with the original quadratic. Over here, this fraction times this fraction, the x minus 2 factor cancels out, but I'm left with the a times the x squared plus 2x plus 4. And this fraction times this fraction, the quadratic factor cancels out, so I'm left with the bx plus c factor times the x minus 2 factor. Okay, so now again we're back to where we were. We just got to be careful about our steps. Multiply out the right-hand side, or distribute the a here, so we get ax squared plus 2ax plus 4a. And then being careful here, using our FOIL method, we get bx squared minus 2bx plus cx minus 2c. Gathering similar terms, the x squared, we get an a and a b. So we have a plus b on the x squared term. The x's, we have 2a minus 2b plus c. So again, I'm going to put a plus and then just put all those values in parentheses. 2a minus 2b plus c on the x term. And the constants, 4a minus 2c. So again, in parentheses, 4a minus 2c. And that all equals this side. So now we can set up our system of equations. We know a plus b has to equal 3. 2a minus 2b plus c must equal 17, and 4a minus 2c must equal 14. So 3 equations, 3 unknowns. We know how to solve this system. So let's see, we got an a and a b and c, and an a and a c, so it's not as easy as the last one. But remember, our first step for these, we choose 2 equations and we eliminate one of the variables. So let's choose, I don't know, let's see, is anything easier than anything else? If we choose 1 and 3, I guess, eliminate the a's, we'll have another equation in b and c, but that's no good. So we have an equation in a and b, we have an equation in a and c. So ideally, we want another equation in a and b, or another equation in a and c. So then we can solve for those 2 and go back and solve for the third. So this one looks like the absolute easiest one, right? A plus b equals 3. So let's use these 2 and eliminate the c, and then we'll have a second equation in a and b. So I'm going to choose, and again, there's choices here. The more you do, the better you are at choosing the easiest way, but it comes with practice. That's why you want to practice. So I'm going to choose 2 and 3 and eliminate the c. All right, so if I eliminate the c, I need to make this a 2c so that I can eliminate it with the negative 2c. So I'm going to take equation 2 and multiply it by 2. to get 4a minus 4b plus 2c equals 34. Multiplying everything in equation 2 by 2, adding it to the third equation, 4a minus 2c equals 14. Okay, so I add those together, I eliminate the c's, I'm left with 8a minus 4b equals 48. And we'll call that equation 4. All right, well now I have two equations in A and B, right? Equation 1 and equation 4. So now solve 1 and 4. So equation 1, a plus b equals 3, and equation 4, 8a minus 4b equals 48. So nice, easy, two equations, two unknowns. Let's use a substitution here. We'll solve a and get 3 minus b. Plug that into 4. And get 8a minus 4b equals 48. Solve this. 8 times 3 is 24. Minus 8b minus 4b, 48. We get negative 12b equals 24. Nicely, b is a whole number of negative 2. Once we know what b is, we can come up here and solve for a. A is going to be 3 plus 2 to get 5, and then all we need is the c. So we can come back here to equation 3, plugging in b equals negative 2 and a equals 5 into equate. Well, actually, all we need is the a equals 5. We don't need the b. So 4 times 5, 4a minus 2c equals 14. 20 minus 2c, negative 2c. If we subtract 20, we get negative 6. So c is going to be 3. So we got our a, our b, and our c. Once again, this is the given fraction. Your answer is this fraction, this sum of fractions with the appropriate values that we just came up with. Positive 5, b was negative 2, and the c was 3. All right, so you're given this fraction, you're asked to decompose it. You go through this process, this is your answer. All right, that's the third case. And the last case is repeated quadratic factors. Again, the process is exactly the same. All that changes is the right-hand side of the equation. So let's look at one of those, and that will finish 5.4. So remember, linear factors get a constant in the numerator, quadratic factors get a linear factor in the numerator. And finally, repeated quadratics. Case for repeated quadratic factors. And this one is explained on page 548. The setup. All right, so here, same question. 2x cubed plus x plus 3 over a quadratic factor raised to the second power. So this is an example of a repeated quadratic factor. Quadratic factor repeated 2 times. So what happens here, as you can see there on page 548, each one of the numerators is going to be a linear factor. So we get one fraction for the quadratic factor raised to the first power and a second fraction for the quadratic raised to the second power, right? And each one of these is going to be a linear factor in the numerator, ax plus b, and then another linear factor here, so we get cx plus d. Okay? So this one actually, well, let's just get to the point, because we haven't, let's see how easy it is. Let's see, because we're going to have 4 unknowns here, and we haven't really dealt with equations of 4, but generally these are going to be really, really simple equations to deal with, so let's see how difficult it becomes. It's the same process. We're going to multiply both sides by the least common denominator. All right, we multiply that side by x squared plus 1 squared. We multiply this side by x squared plus 1 squared. Left-hand side, all we get is the cubic expression. On the right-hand side, we're going to get ax plus b times 1 factor of x squared plus 1. Right? This fraction times this one. We still got 1 factor of x plus 1 in the numerator. One of them is canceled out. And here, both of them get canceled out, so we're just left with the cx plus d. Right? Same process as before. Nothing changes over here. We're going to FOIL this out. We get ax cubed, first terms, outside term ax, inside term bx squared, last term b, and cx and d. Gathering similar terms. Let's see, are there any similar terms? Just a couple. So there's only an a on the x cubed, so see, that's going to be really easy to deal with, right? We already know a is 2. For the x squared, again, there's only 1 term on the x squared. There's no x squared here, so it's a 0, so immediately we know b is 0. For the x terms, we got a and c. So we get a plus c on the x term, and the constants we have b plus d. And over here we still have the same thing, 2x cubed plus x plus 3. So now we can set up the system. This time it's 4 unknowns, but as you can see, it's a pretty easy system to deal with. We already know immediately that a must equal 2. We immediately know b has to equal 0. So these are pretty nice equations to deal with. We know a plus c has to equal 1. And we know b plus d must equal 3. So we got a 4 variable, but notice how simple this is. We already know that a is 2, so we can use that and say 2 plus c equals 1, which means c equals -1. And we already know b is 0, so we know 0 plus d equals 3, which gives us our d of 3. So very nicely here, and we just plug those values in, the a, the b, the c, and the d. So this is the question. You're asked to partially decompose this. You go through that, you solve your system. We get ax plus b. You can put the 0 if you like, you don't have to put the 0. And cx -1 plus 3 is your answer. Good times with partial diffraction composition.